We'll continue with the same problem that we started at target motion analysis. And we'll not only show the solution, but we'll evaluate now quantitatively the number of values for the parameter, and the quality of the estimate will be also described depending on the relative geometry between the platform and the object of interest. We'll use the maximum likelihood technique. We'll write the likelihood function of x, which is the joint probability density function of the cumulative set of observations. There are n observations, say, given x, p of z1 through zn given x. In view of the independence of the measurement noises, we can break it down as the product of the marginal probabilities of each of the zk given x. And each of the zk is Gaussian distributed under the assumption that we have a Gaussian noise, with the argument being z, mean is h of k and x, and the variance is r. Again, in the expression h, we are going to use the four-dimensional parameter vector that characterizes the motion of the object of interest. And this is the mean of the observation. The maximization of the likelihood function is equivalent to minimizing the negative log likelihood function, which becomes a nonlinear least squares problem. X hat is the argument that maximizes with respect to x the cap lambda of x, or the argument that minimizes with respect to x the lowercase lambda of x, where lambda of x is just the exponent with the opposite sign. So there's a negative log likelihood function, and the irrelevant additive constants obviously have been left out. And clearly this is least squares but nonlinear because the function h is nonlinear. There are numerical optimization algorithms which can be used. In this case, the Newton-Raphson or quasi-Newton techniques are very effective, and they are coming packaged in several software packages. And in most cases, what has to be done is just provide the explicit expressions of the derivatives. Okay, once we know what has to be maximized, we would like to get an idea about the quality of the result. Namely, we maximize the likelihood function, we get an estimate how good it is. And we have the Camera lower bound result on the covariance matrix of a parameter estimate, x hat, assuming it to be unbiased, that expected value of x hat minus x times x hat minus x transpose is greater or equal to the inverse of J, which is the Fisher information matrix. So now we are going to calculate the Fisher information matrix, and it turns out that this is the only way in which we can obtain the covariance of our estimate in a nonlinear problem. And what we hope is that if the bound is met, if the estimator is efficient, this is the covariance. So A, we get a bound, B, we evaluate it, C, we compare it with actual results to confirm that it can be used as the actual covariance. And the numerical results for comparison will be Monte Carlo runs, which means it's experiment that can be repeated, therefore it is offline, and what we get out of it is the confidence that the lower bound is achieved, the estimator is efficient, and therefore when we have to run a single real-time experiment, we can use such offline computable covariances with reliability. There is one catch here. The Fisher information matrix does require an evaluation of these expressions at the true value of the parameter. In practice, this is not known. The evaluation will be done at the estimate. So we have some functional forms and we evaluate it at the estimate. And we have to be a little bit careful because estimation errors do have an impact on this, so they can slightly distort the results, but in general they are reasonably reliable. Here is the way we carry out the evaluation of the Fisher information. The gradient of the negative log likelihood function is minus R inverse sum. Here's the gradient of the function x. This is a scalar, del x is a derivative, it's a vector with respect to 4 parameters times z minus h. If you take this and multiply it with its transpose, that's in this expression here, we have this on the next page, we multiply it with itself, transposed. Notice that this is a scalar, this is a vector. And what we have will be measurement case difference between the actual measurement and h. Now, all these appear in the second summation. And what we have is a double summation, but this only when multiplied with the same difference for the same k yield after an expectation a non-zero result, because this is effectively the value of wk, which we don't know. But in the expectation, here we pick up the w's and we use the whiteness, and the double summation will have no cross term, so it becomes a single summation, and all that's left will be these derivatives. The gradient with respect to x of h is denoted by h sub x. So we use this compact notation, and we have these terms give us an r when they are not 0. There's an r to the minus 2, the product gives an r to the minus 1, and the minus is gone because it appears twice. So what we have here again is a sum of dyads, and as indicated earlier in the linear algebra part of this course, in order a dyad has a rank 1. What we need is J being a 4 by 4 matrix, because this is a 4-dimensional column vector times a 4-dimensional row vector gives a 4 by 4 matrix. That's the dimension of the parameter x. We need at least 4 such vectors to be invertible. Furthermore, they should not be collinear, which means they have to span the space. This is the requirement for invertibility. Otherwise, if J is not invertible, J inverse has infinite eigenvalues, therefore the problem is not completely observable. And this is another way of coming up with the result shown earlier using an intuitive argument and simple geometry, that you might have a lack of complete observability. But again, we will not have it if we have the platform trajectory arranged in a suitable manner. So, to summarize it, in order to have parameter observability, i.e. to allow its estimation without any ambiguity, as discussed before, the Fisher information matrix must be invertible. If it's not invertible, it is singular, then the lower bound does not exist. It will have one or more infinite eigenvalues, which means total uncertainty in a subspace of the parameter space. In other words, ambiguity. Infinite eigenvalue is an eigenvector corresponding to it, and this shows the combination of parameters that we cannot estimate for the geometry of the problem as considered. Then the information limit say it's not enough. We have insufficient information in the data. So we've got to make sure that the data we use do provide enough information to estimate the parameter without ambiguity. Next is what we have now, assuming that the Caramera lower bound exists, we have a lower bound of the covariance matrix. But since this is the only expression we can obtain for the covariance, we hope it is the actual covariance rather than just a lower bound. Therefore, we are hoping we have estimation efficiency. Let's look at this. Assume that the parameter estimation error, x tilde, defined as x minus x hat, is approximately Gaussian distributed with covariance given by the Caramera lower bound, namely the covariance P is really J inverse. Assuming now also that J inverse is invertible, we have a positive definite covariance. Now, if the errors are Gaussian or approximately Gaussian, and we have from the CRLB the covariance, and we assume efficiency, the expression x tilde inverse, P inverse x tilde, which is same as x tilde prime, J x tilde, would be chi-square distributed with nx degrees of freedom. This epsilon x is chi-square nx. And this is the normalized estimation error squared. It is a Gaussian random vector divided quadratic form with respect to the inverse of its covariance matrix. This can be shown to be exactly the sum of nx 0, 1 or standard Gaussian random variables squared. So it is chi-square with nx degrees of freedom. Now, we can, in simulations, evaluate this normalized estimation error squared to check whether the estimator is efficient. That is, do the errors match the covariance given by the CRLB? So we are carrying out an efficiency check. The probability for this epsilon x being below g squared is 1 minus q for a certain value of g, and q being a small tail probability. So we set up for a small tail probability, again between 1 and 5%, the threshold below which epsilon x has to be in view of knowing its distribution as chi-square nx degrees of freedom. Again, there is an approximation because the errors themselves, this is a nonlinear problem. Even though the measurement errors are Gaussian, the actual parameter errors are not Gaussian. Nevertheless, they are not too far in most situations, so this is a reasonable assumption. So, the NES will have to be less than g squared with high probability 1 minus q if the estimator efficient. This will be a one-sided probability region. We cut off only an upper tail with mass q for this normalized quantity epsilon sub x. The second is, this will be illustrated in a minute when the results are shown. We also want a confidence region for the target parameter vector. A, we want to satisfy ourselves that the CRLB based covariance is the covariance rather than just a lower bound. Second, now if we do have the covariance, we would like the region in the space where the true parameter lies, because it will not be ever exactly on the estimate, but will be somewhere around the estimate. So we want a multidimensional region because this is a multidimensional parameter estimation problem. So, given the true parameter x one has, if the estimator is efficient, a maximum distance, that's a square distance, the normalized estimation error squared, from it to the estimated parameter. That's a squared norm of the error. Now, if x is not known and x hat has been obtained, one can say that x should be within some neighborhood of x hat, determined by the same equation, and this is the confidence region for the true parameter. So if you have x, you know x hat has to be close to it somewhere. But you don't have x, you have x hat. So now you put the problem backwards. I have x hat, where is x? X is somewhere around x hat. And this is called the confidence region. What is the region? This confidence region will be obtained based on the Gaussian distribution. We have, that's the x tilde, x minus x hat, transpose p inverse x minus x hat equal to g squared. As a geometric curve, this is, in 2 dimensions, an ellipse. In more dimensions, it's an ellipsoid, hyperellipsoid, a so-called G sigma ellipsoid. If you look at in 2 dimensions, you can find that this is the magnitude of the semi-axis. How many times you have the semi-axis, or the axis of the ellipsoid, of the ellipse. So what you have is, because P is positive definite, you have the semi-axis G times the square roots of the eigenvalues of P. And this is a so-called probability concentration ellipsoid obtained by cutting the tails of a multivariate Gaussian density. You set a threshold on the multivariate Gaussian density, which gives you an inequality for the exponent. At that point of the threshold, you have an ellipse. So the boundary is an ellipse, the region is inside the ellipse. What you have is really a normalized distance here, and this is also known as the Mahalanobis distance between x and x hat. It's a weighted norm squared. Okay, now the other thing that is of interest, if you get a position estimate and a velocity estimate at the reference time, that's the output of the problem. What you would like is to map it into a position estimate at an arbitrary time. This is a similar problem to the extrapolation of the polynomial fit that we did earlier. Remember, the motion now is constant velocity. We assume the object of interest does move with a constant velocity, and we estimate its position and velocity, each 2 components in the psi and eta, or x and y coordinates. So take the 4-dimensional estimated vector, multiply it with this matrix that picks up the psi position, psi velocity, the eta position, eta velocity, will map it into 2-dimensional position that is a predicted position. Here P stands for predicted, not for platform. Notation is somewhat ambiguous. So that the predicted location, position, at some arbitrary time t is given by the product of this matrix phi sub pt x hat, which follows from the constant velocity assumption of the target as indicated. Pick up position, pick up velocity in each coordinate separately. The covariance corresponding to the prediction or extrapolation shown above is P only for position, in this case phi pp, phi p transpose, where each of these phi's depend on the time interval for the prediction, t. And there will be a confidence region for the position where we predicted this, again given by an ellipse under the Gaussian assumption that the x position at some arbitrary time will be around x hat pt, according to this elliptical region. This is an ellipse centered at xp, and the covariance and the gp square define it. So gp is the desired probability concentration. It is also called gate probability. You can find the gp for the 95% or 99% typically. So what we have now is that the Camera lower bound quantifies the stochastic observability or estimability, which is not a binary property as in the deterministic case, where we had a linear system. We said this is completely observable or not completely observable because we take a deterministic matrix which is singular or non-singular. That's a black and white situation. Now we will face gray situations. In practice, the lack of invertibility of J, which might be just ill conditioning, indicates that the parameter is unobservable. So the way a computer comes back to you without to invert a matrix, I cannot do it. Why? Because it's ill conditioned. Matrices with eigenvalues 8 or 10 orders of magnitude apart are not nice, and computers will not provide you an inverse. The condition number, which is really the ratio of highest to lowest eigenvalue, is too large. That is a problem. If J is invertible, but the position confidence is large, again, what large is, it's subjective. What we can say, we have marginal observability. And this occurs if the gradient vectors, which are in the dyad, some of those dyads in the Fisher information matrix, are nearly collinear. Then you have one or more eigenvalues that are quite large and others which are reasonable, even though the whole thing is invertible, but you might not be satisfied with the results. A small confidence region, good observability, is obtained if those n gradient vectors in those dyads, again, span well, quote, well, unquote, the nx dimensional space, that is, they are far from being collinear. They point in all directions, pretty much. The actual measure of this is the condition number of J, again, largest to smallest eigenvalue ratio. He will show now how we evaluate from Monte Carlo runs whether our estimator is efficient. So, the practical procedure, which we'll illustrate very soon, to check the estimator efficiency is using Monte Carlo simulations. We have epsilon sub x I, the normalized estimation error squared, in a run I, and we say have n runs. From these n runs, all with independent random variables. We generate the noiseless observation, we generate the noisy observations, and we carry out the estimation, and we have the error by comparing the estimate to the true value. So what we do is we'll calculate an average NES from these n independent runs, take this epsilon xi, sum over n and divide by n, and get an epsilon x bar. Now, before dividing with n, what we have is this summation on the right-hand side. Because the Monte Carlo runs are done with independent random variables from one run to the other, we have each epsilon x as a nx degree of freedom chi-squared. The sum of n such independent chi-squares is an cap n times little n sub x degree of freedom chi-square distributed random variable. Now we define the 1 minus q two-sided probability region for n epsilon x bar as the interval epsilon 1 prime to epsilon 2 prime. So this is on the, if nx is 4 and say n is 25, that's 100 degree of freedom chi-square. And we define for this 100 degree of freedom chi-square an interval. And this is the epsilon 1 prime with the q over 2 left tail, and epsilon 2 prime, the point with the q over 2 right tail, upper tail. Here's the example, nx4, n25, 5%. The expected value of this is, by the way, 100 because it's a 100 degree of freedom chi-square, but it's not quite symmetric. The upper 2.5% tail starts at 130, the lower is below 74. So what we have is the region for epsilon x will be obtained by dividing these numbers with n. So 74 over 25 is approximately 3. 130 over 25 is 5.2. So this is how the relationship between epsilon I prime and epsilon I can be written, both upper and lower bound. And once this is done, we can check whether the epsilon x bar, which is the average normalized estimation error squared over our n runs, is efficient. So the epsilon x bar, is it in the epsilon 1, epsilon 2 region? It should be, with high probability, say 95%. If it is, we say yes, we accept the hypothesis that the estimator is efficient. If it's outside, we reject it, even though with a small 5% probability tail, that's what we did here, Q 5%, we might make a mistake. It means, by bad luck, the random numbers were too large and they ended up outside. But we have to take this chance in all decisions that have to be made using random quantities. Here's the example. This is a localization example to illustrate the problem of estimating a four-dimensional parameter that tells us everything about the motion of a constant velocity target in a plane based on bearings only, or angle only, line of sight angle only observations. The true parameter vector is, object is away 10 kilometer, 20 kilometer, x velocity or psi velocity is 0, y velocity is minus 10 meters per second. We make bearing measurements with standard deviations of 1 degree from a sensor on a moving platform every 4 seconds over a total period of 15 minutes. And the measurement noises are independent, identically distributed Gaussian with mean 0, and this is their standard deviation. We have two scenarios. The distinction between them is the trajectory of the platform. Here is scenario 1. The platform moves northeast, then northwest. The target of interest moves in this direction. These will be the measurements in one particular run. So let's see the second scenario. Now this is the true trajectory for the object of interest, the target, and this is the motion of the platform, northeast, then southeast. So the target moves over those 15 minutes from the initial location. At the same time, the sensor moves in a two-leg constant speed trajectory with the northeast, northwest, and the northeast, southeast. Now, we also will go back to these figures and see the 95% probability mass ellipsis along the target's initial and final position based on the camera lower bound. So this will be ellipsis centered at the 2x. Because of simulation, we know the 2x, and the x hats should be inside these ellipses for the position at those particular times, and we have initial and final time. We obtain the CRLB for the initial position, and we map it, as shown before, based on the initial position and the constant velocity. We map this to a final position. So these are for geometry, that's called scenario 1. This is the relative geometry, and you can see this is the ellipse at the initial position. It's pretty large. At the final position, it's substantially smaller. Nevertheless, the ellipses are not very large, but given that only passive angle measurements are made, this is the best that one can obtain. So there's one outcome here of an estimated trajectory based on these measurements. Here's the second geometry. And look at the difference. The northeast and southeast motion for this two trajectory give us much larger ellipses. This is a marginal observability situation. The maneuver, the change of course, as illustrated in this second scenario, was substantially less beneficial in terms of information gathering, and the CRLB-based ellipses quantify this result. So what we have is those 95% ellipses, both at initial and final position, and here is an enlarged version of the first one. We have this ellipse. This is the initial position. This is the final position. And in each ellipse, what we have is plotted estimated target position in 100 runs for this first scenario, which means 100 Monte Carlo runs were carried out. In each, independent noises were generated from run to run, and also independent across time because the noises are white. We get 100 initial position estimates, initial velocity estimates. We plot the position estimates here. We map the initial position and initial velocity estimates to the final time position estimates and plot them inside these ellipses. And hopefully they will end up inside the ellipses, but as you can see, pretty much these are indeed inside. So this is scenario one. And a more detailed, enlarged version of this will show that the 95% ellipses for the position contain all but 3 of the estimated positions. It's an acceptable deviation from the 95% to get 97% of the 100 outcomes. Obviously, if you make 1,000, you'll be closer to the 95%. Now, another evaluation that's of interest is this was the graphic evaluation of whether those ellipses are representative of the actual spread of the estimated values. Second is the statistical test using the normalized estimation errors from 100 runs, which should be theoretical value is 4. You can calculate a confidence region for it about 4 based on the fact that it's 100 degrees of freedom chi-square. So you end up with this as 3.87, which is well within that confidence region, which was approximately 3 to 5.2. So that region, between 3 and 5.2, is the region within which it has to lie with 95% probability. We find it well within the region, and this confirms the validity of the CRLB as the actual covariance for the present problem. And remember, this is the only covariance you can obtain in this case. So it's very important that the CRLB is useful not only as a bound, but as an actual value. So the hypothesis that the estimator is efficient can be accepted.